Welcome to this episode in the Relativity series. Today, we're exploring one of the most fascinating concepts in astrophysics, the event horizon. This is the boundary around black holes that represents a true point of no return. Once anything crosses this invisible line, escape becomes impossible, even for light itself. Let's dive into understanding what makes this boundary so extraordinary. So, what exactly is an event horizon? An event horizon is the boundary surrounding a black hole beyond which nothing can escape. Think of it as an invisible sphere around the black hole. Once anything crosses this boundary, it is pulled inexorably toward the singularity at the center. There's no way back. Not for matter, not for energy, and not even for light. This makes the event horizon one of the most extreme boundaries in the universe. The event horizon truly is a point of no return, and here's why. Outside the event horizon, escape is still possible if you have enough energy. You could fire your rocket engines and get away from the black hole's gravitational pull. But inside the event horizon, the situation changes completely. No escape is possible, not even for light. The gravitational pull becomes so intense that all paths, no matter which direction you try to move, lead you deeper into the black hole. To understand why nothing can escape from inside an event horizon, we need to talk about escape velocity. Escape velocity is the minimum speed needed to break free from a gravitational field without any further propulsion. For Earth, this is about 11 kilometers per second. But at the event horizon of a black hole, the escape velocity equals the speed of light, which is 299,792 kilometers per second. Since nothing in the universe can travel faster than light, this represents the ultimate limit. Nothing can escape from inside the event horizon. The size of the event horizon is determined by what we call the Schwarzschild Radius. This is the radius of the event horizon for a non-rotating black hole. The formula is R sub s equals 2gm divided by c squared. Here, g is the gravitational constant, m is the mass of the black hole, and c is the speed of light. This elegant equation tells us that the size of the event horizon depends directly on the mass of the black hole. The more massive the black hole, the larger its event horizon. Let's look at some concrete examples to understand the scale. If we compressed Earth down to a black hole, its event horizon would have a radius of only about 9 millimeters. That's smaller than a marble. Now, if we did the same with our Sun, the event horizon would have a radius of approximately 3 kilometers. These examples show us just how incredibly dense black holes are. All that mass compressed into such a tiny region creates the extreme gravitational field that forms the event horizon. Several extraordinary phenomena occur at the event horizon. First, time dilation becomes extreme. Time appears to stop for an external observer watching something cross the boundary. Second, light becomes infinitely redshifted and dims to darkness, making the object invisible. Third, the event horizon is a one-way surface, a mathematical boundary that can only be crossed in one direction. And surprisingly, nothing special happens locally when crossing it. There's no physical wall or barrier. An observer falling through wouldn't feel anything unusual at that exact moment. Once inside the event horizon, the fate of anything is sealed. All paths lead inevitably to the singularity at the center. Collision with the singularity is unavoidable. Here's where things get truly mind-bending. The singularity becomes part of your future, not a place in space. Inside the event horizon, space and time actually swap roles. Moving forward in time means moving toward the singularity. You can no more avoid reaching the singularity than you can avoid moving forward in time. One of the most fascinating aspects of event horizons is that different observers experience dramatically different realities. An outside observer, watching from a safe distance, sees an object freeze at the event horizon. They watch it appear to slow down and fade away as the light redshifts. But the falling observer experiences something completely different. They cross the event horizon in finite time. To them, their own clock ticks normally, and they experience nothing unusual at the crossing itself. This stark difference in perspectives is one of the most counterintuitive predictions of general relativity. Let's recap the key points. First, the event horizon is the boundary where escape velocity equals the speed of light. Second, once crossed, nothing can escape. It truly is a point of no return. Third, the size of the event horizon depends on the black hole's mass, calculated using the Schwarzschild Radius formula. And fourth, different observers experience dramatically different realities when it comes to crossing the event horizon. The event horizon remains one of the most fascinating predictions of Einstein's general relativity, showing us just how extreme the universe can be.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.